ఇది కూడా అవసరం లేదు పని పెడితే వచ్చి
కింద మనం చూసుకోమని మధ్యలో వెళ్ళినప్పుడు షెడ్యూల్ పెట్టలేదు కదా మళ్ళీ దాన్ని కట్ చేయాలి మనం.
అవసరం. హలో हाँ unmute. I could.
Hey, hey, yes. La 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 la. It's good. Thank you. So before we start, can I ask who knows about parity games? Okay, I was gonna give a long introduction. No, that's unnecessary. I will still give some. So hello everyone, I'm Irmak Salam, and this is joint work with my advisor, Anna-Katrin Schmuck. And here we give an efficient algorithm to solve something we call odd-fair parity games. These are parity games under some specific fairness condition that I will talk about. So I will first give an introduction to parity games. Then I will introduce this fairness condition and odd-fair parity games, which are just parity games under this fairness condition. Then I will mention some existing methods that solve such games, and I will introduce our Zielonka type algorithm that solves such games, which is the first efficient algorithm to solve such games. And then with experimental evaluation, I will try to convince you that it's actually efficient. Where should I point this? Okay, so I will start with parity games. Sorry, where should I point this at? Oh. Okay. So parity games are two-player games played on a finite graph. The nodes are divided into two players, namely the square player and the circle player. Okay, I need to learn where to point this at, or it doesn't work. Where is the...
This method.
I know, but like, where should I point this at so that it changes? There?
Imagine on this.
It's here.
So you're pressing.
Okay, this is better, maybe. Here. Sorry for, okay. I think that works. Okay, I will do this. Okay, so the nodes are divided between two players, square player and circle player, and the play is just we assume that there are no deadlocks, and the play is just an infinite trajectory drawn by the token being shifted from node to node by the owner of the respective node. For an example play is this pi. We start the token from V1, and now the square player decides to either take the self loop and leave it at V1 or to carry it to V2 or V3. Let's assume it carries it to V2. Now the circle player decides what to do with it. Let's say it takes the self loop for once and then decides to shift it to V3 and then to V4 and so on and so forth. So this is a play. And in parity games, we have a winning condition called the parity condition. And for this, our nodes are also labeled with some priorities or some natural numbers. And the winning condition says that one of the players, called the circle player, wins if and only if the maximum priority seen infinitely often in the play is even, and the square player wins if it's odd. So that's why we also call these players even player and odd player. Okay, so let's now look at this play. After some time, only 3 is seen in this play, so the maximum priority seen infinitely often is odd, and that's why odd player wins this game. And so let us look at this choice of edges of the circle player. Let's say whenever the play comes to V2, it decides to first take the self loop and then take it to V1. And whenever the play comes to V3, it just throws it back to V1. So with this choices of edges or this strategy, the circle player or the even player can actually win the game from the node V1 and actually also from V2 and V3. And that's because, so if we look at an exemplary play that starts from V1, then what the square player can do, then it can take the play to V2, and then from V2, circle player first takes the self loop and leaves it at V2, and then takes it to V1. Then V1, let's say, takes it to V3, then V3 shifts it back to V1, and so on and so forth. And no matter what the square player does, the priority 4 will be seen infinitely often. And since this priority is even and bigger than all the other priorities, this play will be won by the even player. So this is called a winning strategy for the circle player. And there is an important property of the parity games that they have positional winning strategies, which means whenever one of the players is winning from a node with some kind of a strategy, it also wins from that node with a positional strategy. And a positional strategy is just a strategy that fixes one outgoing edge from each node of this player. And whenever the play comes to this node, this player must take this edge. So, for example, in this play, the circle player can just instead choose to shift it back to V1 whenever the play comes to V2 and take only the green edges. And this will be a positional winning strategy for the circle or even player. And in fact, we can show positional winning strategies with a subgraph from which the winning player has exactly one outgoing edge from all of its nodes, and the losing player has all of its outgoing edges. Okay, and this having positional winning strategies actually puts parity games into MP intersection co-MP because, yeah, let's say I assume that the circle player has a winning strategy, then I can just guess a witness that's of this shape, and then check if all the cycles are even, if all the cycles have the maximum priority of even, and yeah, if it does, then I can verify it in polynomial time, and it's in co-MP because these games are symmetrical. I can do the same for the other player as well. And also, these games are determined, meaning that each node has exactly one winner. Each node is won even by either by even or by odd. And this gives us the winning strategies for even and odd. We can divide the whole state space into the winning region of even and winning region of odd. And actually, when we mention solving a parity game, what we mean is finding these different winning regions. And thanks to their positionality, there are many efficient algorithms that solve parity games, which makes parity games a canonical game to be used in correct by design software or hardware synthesis. And so if you have another game that comes from some design problem, you can typically convert it to parity game and use one of the off-the-shelf tools that are efficient to solve it. And yeah, this makes parity games very important in practical scenarios as well. And one canonical algorithm that is used is Zielonka's algorithm. While Zielonka's algorithm has exponential complexity, and there are actually algorithms that give better complexities, like quasi-polynomial algorithms, they are shown to be not so good in practice. And in this talk, what we aim to give is also not better complexity bounds, but better efficiency for our kind of games, which I will introduce next. So since Zielonka's algorithm is such a canonical algorithm, it is accepted to be the best working in practical scenarios, we will try to mimic Zielonka's algorithm for our kind of games in order to find an efficient algorithm. Okay, so now I will introduce strong transition fairness. In strong transition fairness, we are given a game graph. And with this game graph, we are given a subset of its edges, which we show by the dashed lines on this example. And the strong transition fairness constraint asserts that whenever one of the source nodes of this live edges are visited infinitely often, this live edge should also be taken infinitely often. And one more constraint is that the source nodes of these live edges always belong to only one of the players, and without loss of generality, we will assume here that this is always the square player. And for example, in this example, the square player is not allowed to always take the self loop on V4, and it should eventually progress to V3. And similarly, it's not allowed to always take the other edges in V1, but if it comes to V1 infinitely often, it should eventually take the self loop infinitely often as well. So this fairness constraints first came up from abstraction-based control design, but they're also found widespread in planning and even resource allocation problems. So even though they have limited power, they are somehow widespread. And now we look at parity games under this fairness constraint, and we will call them odd fair parity games. Now we put this liveness constraint only on the odd player. And why is the liveness constraint only on one player? It's because usually we identify ourselves with the system and the other player with the environment, and we somehow want to limit the behavior of the environment to make it more realistic. So let's say like we are the circle player and square is the environment. And now we want to limit the behavior of the environment. Now the odd player wins in the scenario if and only if both the maximum priority seen infinitely often in the play is odd, so that's the parity condition, and the play obeys the fairness condition. So odd player loses all plays that are not fair with respect to this fairness condition. And if you look at this example, now I have inherited the dashed lines from the other example. So now this winning region was the old winning region without the live edges. Now the winning region of even actually expands. And that's because square play is not allowed to stay in V4 infinitely often, and it should eventually progress to V3, and from V3, circle has a winning strategy. So this condition increases the power of even. And now, just for the sake of making it winning for odd and seeing what odd strategies look like, let's tweak the example a little bit and change this priority 1 with 5. Now the maximum priority in the game is 5, and now actually all the game is won by odd. That's because this V1 node owned by the odd player can always force it to V2. However, now the odd player does not have a positional strategy, because in case the game always comes back to V1, it should always take its self loop. So we cannot assign only one outgoing edge and say, okay, always take it, because if it only takes the self loop, then it will be losing. However, the even player still has positional strategies, since the live edges are only defined on the odd player. And in fact, this is a winning strategy for odd. If the odd player always takes, let's say, alternatingly the self loop on V1 and then shifts it to V2, no matter what the circle player does, it will be winning. And from V4, it can take the self loop, it can go to V3, it doesn't matter, it always wins. Okay, so odd player does not have positional strategies, but we need some characterization of strategies to be able to make the proofs go through. And so we define something called almost positional strategies. And I will introduce it next. So like we have defined positional strategies in terms of some subgraphs, we will also define these almost positional strategies in terms of some special subgraphs. So now let's see the positional strategies again. Even still has positional strategies. So this was the example that was won by even. Now all the odd nodes have all their outgoing edges, and even nodes have exactly one outgoing edge. This is a positional strategy subgraph. And for the odd, we have almost positional strategies, meaning still the even has all their outgoing edges, meaning no matter what even does, it doesn't matter. And for the odd nodes, all the odd nodes either have one outgoing edge, or it has all their live outgoing edges and plus possibly one more edge. And this is enough for them to win. And if they do not lie on a cycle, then they have exactly one outgoing edge, meaning they still have a positional strategy, because if they do not lie on a cycle on this subgraph, then this means that plays starting from anywhere in this graph just only passes over them once. And that's why they do not have to obey the liveness condition, and they have a positional strategy. And if they do lie on a cycle, then they need to possibly take all their live outgoing edges, and all the cycles drawn by their live outgoing edges should also be odd winning. And that's why, so we have this characterization. And you can see here in V1 node lies on a cycle, so it takes all its live outgoing edges, meaning the self loop, and then it also takes one more additional one to V2 to be able to win. And for V4, actually it also lies on a cycle, and it takes all its live outgoing edges, but it doesn't need another one. So. Yeah, and the interpretation of the subgraphs, which is trivial in the case of the positional one, but that the winning player only takes the green edges in the graph, and whenever a node is visited, it takes all its green edges alternatingly, or equivalent, you can say infinitely often. It takes all of them. Okay, so now because odd-fair parity games don't have positional strategies, we cannot just use the off-the-shelf tools, or they do not translate very easily. But there exists a known method to solve odd-fair parity games, which I will briefly mention as existing methods. So this is a recent paper by my advisor and others, that they give a fixed point characterization of the winning regions for odd-fair parity games. However, fixed point calculations become intractable very easily, especially when the number of priorities increase, etc. So there exists no efficient algorithm known so far before this talk. So we give a Zielonka type algorithm to solve these games. And for this, we use the almost positionality characterization of the odd strategies. But this will not be explicit, but yes. And our algorithm preserves the structure of Zielonka's algorithm, which I will show next. And it only minimally increases the number of attractor calculations in Zielonka's algorithm. So, yeah. And we will also show that it gives very similar results with respect to fixed points. So this is what Zielonka's algorithm originally looks like. And for those of you who don't know, so there are two recursive algorithms. One is this. One is solve even and one is solve odd. And this, if we have a game, let's say with the maximum priority even, we can give the maximum priority here as an input and the game here. And ignore this. And here the algorithm takes the set of the nodes with the maximum priority and then calculates the attractor of even to these nodes and isolates this. And then this solves the rest of the game with the maximum odd priority that is remaining. And then, yeah, after this is done, now it computes the odd attractor set, and then this corrects the calculations. And this is our variant. Only the colored lines have changed. So we used to have only the safe reachability for even, the attractive composition for even here. Now we have another formula, which I will give soon. And then we used to have X here, but now we have a linear computation of the attractor of odd here. So in the odd formula, this attractive composition of even was a one-nested fixed point formula, or just an linear computation with one attractor computation. And in our version, this is just another one-nested formula, another linear formula. But now we have two attractive compositions. So this is what we mean by minimally changing the steps. But this doesn't really add much. Since this is a very cheap computation. And for the safe reach odd, this is already the old safe reach odd. We only add an additional one. And this is also only a one-nested formula. So we add a one linear computation here. And these are just one-step attractor computations, so they are cheap. Yes, and the experimental evaluation we did. So this is a log space graph. In the left-hand side graph, we compared Zielonka's algorithm, the original one for parity games, with the fixed point algorithm for parity games. So Zielonka's algorithm is better. And here we have odd-fair Zielonka's algorithm with the fixed point algorithm for odd-fair parity games, which we got from this previous paper that I mentioned. So yes, so the conclusion is that the odd-fair Zielonka's algorithm preserves the algorithmic advantage of what Zielonka's algorithm have over the fixed point calculation. Yeah, so we kind of say that we mimic Zielonka's algorithm and we somehow preserves the whatever is good in zero-case algorithm, we preserve it. And I think I'm first. So in conclusion, in this work, what we contribute is that we give the first characterization of the winning strategies in these games. And we also give the first efficient algorithm to solve such games. Thank you, and I will be happy to take questions.
Thank you very much for your talk. Other remark or questions?
Yes. Oh.
Can you hear me? So in one slide where you showed the winning region of the even player, can you just go to that slide? Maybe I missed something. Yeah, this one. Yeah, so here you're saying that this is the winning region for even, and the condition is that if, let's say, for the square state with parity 4, if this state is visited, then the dashed edge should be visited. I mean, if the square state is visited infinitely often, then the dashed edge should be visited infinitely often, right? That's the winning condition.
Yes.
So how is this winning for the even player? Because if from 1 and 3, if it chooses the edge to 4, the environment could always come back to 1 and 3 and never visit the dashed edge, right?
Oh, but the environment is the square player. The circle wants to make it even, and the square wants to make it odd.
Okay.
Right? So you meant like if we start the self loop, right? Sorry, 1-3 loop, right?
Yeah.
But there's a circle loop. Circle wants to make it even. Circle will take it back to V1.
Okay.
Yeah, it's a bit confusing.
Okay. And the other question is that, so you mentioned that this notion of fairness comes from ABCD, that is abstraction-based control design. Can you just explain that as well? Like, can you explain how the motivation for fairness comes from ABCD?
Yeah, I don't know.
Oh, okay.
I don't know. It just first came up from a problem of Koshik and Anna, and they were trying to turn this into discretize it, and then they found out this fairness condition. And then we found out that this is actually widespread in many different areas as well. It was lucky. Yeah.
Thank you.
So are there known quasi-polynomial algorithms for odd fair?
Yes, because they have a nested fixed point that looks just like parity. So just by the applying this fixed point result, nested fixed point calculations have quasi-polynomial. So yes, they also have quasi-polynomial. Okay.
About the benchmarks, do you generate them yourself or okay?
Oh, no. I mean, benchmarks we take. Sorry, the algorithms we wrote from the beginning, we didn't use any efficient things like OINC, etc.
No, about the experimental
benchmarks. No, we use the Syntcom and Cadence. These two we use.
Hi. So I'm just wondering if you can translate it into a bigger parity game. Like,
yes, very good. Yes, you can.
You can? Okay.
Yeah.
Any other question?
Can you express this fairness with the probabilities?
Yes. Actually, this is almost sure winning in stochastic games. So yes, if you just put some probabilities, any probabilities on these dashed lines, any non-zero, and actually, I mean, in stochastic games, you have you don't have normal edges, right? You only have probabilities, and then if you have stochastic games, you can turn all the non-zero probability edges into these dashed lines, and then solving it for almost winning will be equivalent to solving this.
Okay.
But to convert this to stochastic games, you need to make the game graph bigger, but you can still do it with a linear increase in the number of nodes.
Okay.
So it's
So here your fairness constraint only talks about neighborhood direct. If you would like to say something like, if this formula holds, then this other set of formula will be fairly satisfied. Would this be or like can you reduce it to your setup?
What do you mean? The other formula?
Yeah, so here instead of saying that if I touch V4
Mhm.
infinitely often, then each of the outgoing fair edges should be taken infinitely
Yes.
often, yes? And now if you wouldn't talk just about the successor states, but like about some other states in the graph.
Yes,
Yeah.
very good
So-
question. Thank you. So we tried to extend it. So of course, in all general, it goes to street. So this is a lost case. But we tried to extend it only a little bit more and go to something called group fairness, which is still actually kind of local. But we say that, okay, these nodes, we have source nodes, and these are the source, these are the outgoing edges from them. And then we say, if we visit some of these source nodes, can we visit some of these source edges infinitely often? And even that becomes NP complete or like co-NP complete. Yes, so you cannot even extend it a bit further as far as we have seen. Yes, yeah, even we have like a very simple example. So it's a lost case. No, it is determined. It just becomes co-NP complete. I mean the condition that I mentioned. But actually, if you put these live edges on both of the players, then it's not determined anymore. Yes.
Any other question? So let us thank the speaker again. Thank you.
Yeah. This is my friend, and he will present now. This is mine. This is not mine.
Hello, does that work? Yeah.
Okay, and the last talk of this session is given by Mir Vanwala, and the floor is yours.
Yes, thank you. Good morning. I'll be talking about robust positivity problems for linear recurrence sequences. And to begin with, well, I think I need to stay, close enough here. Motivation comes from the world of linear dynamical systems. So here we have a scenery. You can imagine this as sky and water, and you can imagine this point S as the vector coordinates of a drone, maybe. And we have a model of the system. We have for some input control settings, we have that at the next step, the position of the drone goes from S to MS, where M is a matrix transform. And well, subsequently, it can go to M square S, M cube S, M to the 4S. So you have this entire trajectory this takes. And since this is a linear dynamical system, you can ask questions about the trajectory such that, does it always stay above the water? Does it never go underwater? Or does it go underwater? Whoops. Okay, all the way again. Yeah. Does it go underwater only finitely often? And so this is a linear dynamical system. It is a mathematical primitive to verify cyber-physical systems like this one, verify economic models, biological systems, and even stochastic systems. So the practical concern here is, okay, you have maybe this drone, maybe some other thing you want to control in a real world environment, maybe some other thing you want to model, but you have your model, but is this initialization known precisely? And in the real world, you don't want your systems to be safe just so. You want safety margins. So whatever properties you're interested in, does it stay above water? Does it go underwater only finitely often? You want these properties to be satisfied robustly. So that's why one way to do this robust satisfaction is to reason about neighborhoods of S. So instead of this, the picture looks something like this. So here we have a cloud kind of neighborhood here. And in our paper, in our talk, in our discussion here, our neighborhoods are of this mathematical form here. The statistically astute among you will have recognized this as the Mahalanobis distance. It's a slight generalization, if you will, of the Euclidean epsilon ball. So here we have S prime is close to S if it satisfies this condition here. So if you want to express it as an epsilon ball, you have sigma inverse is this diagonal matrix of 1 over epsilon and so on. So we can ask, do all points in the neighborhood initialize trajectories that avoid the water? And as an aside, you could think of this entire linear dynamical landscape as a generalization, as well, just a halting problem for linear update programs. So you can think of this underwater as staying underwater, going underwater as a loop guard. You have a vector of variables S, and your vector of variables is updated in a linear fashion. So you want to verify these programs. It's the halting problem for these programs, and you want to verify it robustly. So that's the scenario. So now we say that the neighborhood goes underwater only finitely often. And how does one interpret this? So one way to do this is interpret it uniformly. So there is a particular threshold beyond which the entire neighborhood is guaranteed to stay above. And this is a strong condition. One could have the weaker non-uniform condition, which says that each of the individual points have a specific threshold. And since this is an entire neighborhood, there are uncountably many points, and these two are indeed like markedly different notions of robustness. And some of the techniques are common. Some techniques have to be different because of the differing perspective each of these two take. So what we'll deal with is an equivalent encoding of the setting. So instead of a full matrix formulation of the linear dynamical system, we'll deal with linear recurrence sequences. So an LRS, for short, of order K is this infinite sequence of numbers. So U0, U1, U2, just like we had a sequence of vectors, here we have a sequence of numbers satisfying this recurrence relation here. So for every n, the term is a linear combination, a fixed linear combination of its previous k terms. So if you specify this recurrence in terms of the constants a0 up to ak, and the initial k terms u0 up to uk, then you have uniquely defined your linear recurrence sequence. And as the linear algebra works out, the setting I showed you in terms of the scenery and this primitive linear recurrence sequence, they're actually equivalent. So here's an example. You have this matrix M. You might recognize this as, this is a scaling times a rotation. So you rotate by some angle here. This is like cos inverse of 4 over 5. You rotate by this angle and you scale by 5. That's the matrix, and your vector S, you start from the x-axis. So you can imagine what it looks like, and you're interested in S, M to the S, and so M to the N, S, and so on. And you're interested in the first coordinate of each of these sequence of vectors. So let U0, U1 be this sequence. You just take the first coordinate. So linear algebraically, it's S transpose M to the N S, because S is just the elementary unit vector. So here's the recurrence here. U0 is 1. It's not very difficult to see. U1 is 4. And if you're good at linear algebra, you can deduce this recurrence. So UN plus 2 is 8 UN minus 25 UN minus 1. So the trick here is to calculate the characteristic polynomial from the determinant of lambda I minus m. This is so far elementary linear algebra. Come on. Okay. And the nice thing about linear recurrence sequences is that they have a familiar closed form that you can work with if you're good at real analysis and so on. And this closed form is also solved for with standard algebra. So for this particular linear recurrence sequence, it is 5 to the n times cos n theta. And in general, also for general linear recurrence sequences, you can always find such a recurrence for a matrix formulation, and you can always find some exponential polynomial that looks like this. So this sequence here, you can express as H transpose M to the NS. So this just says that you are on one, but this H transpose M to the NS tells you where you are with respect to a hyperplane. And you can simplify that to P transpose Qn. So P is a fixed vector that depends on the S you start from. So P is fixed, and Qn is this nice sequence of vectors that depends on your closed form solution. So when we write it out this way, on the right here, so the inner product of PQn, P transpose Qn, looks like P1, P2, that's fixed. That depends only on your initialization. And this Qn is just simply 5 to the n cos theta and 5 to the n sine theta. And the claim is you can always express an LRS like this. And so from the scenery, we went to LRS, and from LRS, we'll be focusing on this particular closed form expression that's nice to work with. So here's a summary. So there's a direct correspondence between scenery and LRS. So for LRS, we will deal with the positivity problem, which just asks, are all terms of the LRS non-negative? And ultimate positivity, are there only finitely many negative terms? So here's the closed form for the LRS. It's the inner product of U and of P and Qn. And positivity and ultimate positivity here are number theoretically hard problems. So so far, I haven't told you about what the status is of these decision problems. So the current state of the art, unconditionally, is that these problems can be solved up to order 5. So if your LRS is of order 5, or the dimension of your matrix is 5 cross 5, then these problems can be solved. And there are number theoretic hardness results at order 6, which I will discuss further in the talk. So if you already for fixed points, these are already hard, and here we're dealing with robust problems. We are giving a neighborhood explicitly, so we don't want to set our expectations too high for these particular problems, these particular variants we're dealing with. Also worth mentioning is that if we make certain spectral restrictions on the matrix, for example, if we assume that this matrix here is diagonalizable, then we can solve ultimate positivity, but not constructively. So we can't actually give an n beyond which everything is positive. And for just positivity, we can solve it up to order 9. So that's the state of the art. These results have been known by Watnin and Worrell since 2014. So, so how do we just begin to approach this? So for all R, you take a particular n, and is the neighborhood positive? Is the entire neighborhood positive for this n? So this means that for all R such that, R is a small enough disturbance to P, the inner product of P plus R with Qn is positive. If this holds, then the entire neighborhood is positive for that particular n. And since we can observe that this sigma is, we assume that it's positive definite, this whole neighborhood is symmetric about the origin, we can rephrase this as the inner product of P and Qn is the maximum over the entire neighborhood of the inner product of R and Qn. And on the surface, this looks weird because this, as we saw in the picture, this neighborhood was this pink ellipsoid kind of thing. So how do you optimize this kind of thing over the neighborhood? Well, this is where some linear algebra tricks come into the picture. So we just map this ellipsoid to the unit ball, and this is a simple linear transform. So max of the inner product of R and Qn is the same as the max of D times BQn. So this B is a known, we can compute this B as a known matrix transform. And Qn is this nice, Qn also has a nice form thanks to our exponential polynomial solution. So now D is over the unit ball, the Euclidean unit ball, and now we know how to optimize stuff over the unit ball. So if you want to maximize the inner product of D and F, where D is in the unit ball, you simply align D along F, and the maximum value is the norm of F. So this is the norm of F, just simply the square root of the sum of squares of each of the entries. So putting it all together, this is, we want the inner product of P and Qn to be bigger than this, which is going to be bigger than 0 because it's a norm. And this also has a nice form here. B, we know B, Qn is of a nice form. So to solve robust positivity problems, the uniform robust positivity problems, this is our strategy here, which says we have this Un and we have this Vn. And it turns out both of these are linear recurrent sequences, and we want to solve the positivity problem for each of these. So for the former, UN, we can use the state of the art because we're going to be in low orders, and the state of the art already knows how to solve this. But for the latter, this gives us sequences which the state of the art can't directly handle. So we need to develop some new techniques, just look into the details of what this LRS looks like, because if UN is of order 4, then Vn is going to be of order 9 or 10, as the linear algebra will work out. So we need to look at this very carefully. In several cases, the state of the art works. In some critical cases, it doesn't. And for the non-uniform version, it's slightly different here. So in the non-uniform version, we want each of the points in the neighborhood to be ultimately positive on its own. We don't want the uniform threshold. So as it turns out, the set of points, the set of all initializations that are ultimately positive has a nice over approximation that comes from the first order theory of reals. So in our cases, it typically would look like, just a half space separated by a hyperplane or a cone. And well, we kind of just need to, the first step is to ensure that our neighborhood is entirely contained within this over approximation. And once we've verified that, there can be corner cases where, it touches the surface. This is literally a boundary case because of the way the geometry works out. And if the boundary case is just a single point of tangency, like in the first or the second picture, then again, we can use the state of the art to resolve the corner cases. But if it is like, if the ball is nested in the cone, then it is non-trivial, but we'll show that we can indeed resolve this case as well. So at the core of executing all these plans, I'm not going to show you all the cumbersome linear algebra or the arithmetic that goes into it, but at a very high level, whether you can execute these plans depends on whether you can resolve this inequality right here, which is 1 minus cos n theta minus phi less than gn, where gn is asymptotically 0. So when does this have a solution? When does this have infinitely many solutions? And it's important to answer this question because in a way, these solutions correspond directly to the indices at which ultimate positivity or ultimate positivity is going to be violated for a point. And well, because gn goes to 0, to solve this, you intuitively want n theta minus phi to be close to a multiple of 2 pi. So, well, here's a picture for you. We'll take a simple case. We'll just forget about phi for the time being. Just 1 minus cos n theta is less than gn. This, well, as the mathematics works out, this generalizes. We have the technology to generalize this. So you have theta, you you just go around the unit circle. Here's, I've drawn it up to 8 theta. And then you have shown an n for which n theta is very close to a multiple of 2 pi. So the burning question here is, how close can n theta get to a multiple of 2 pi? And it is at this point where we're ready to appreciate the number theory that's inherent to this entire problem, which is Diophantine approximation. So this branch of number theory, which, among other things, it's wants to approximate irrational numbers through continued fractions. It's this branch of number theory that gives us both the technology for our decidability results as well as a yardstick for our hardness results. So what's it about? We had theta over 2 pi, we'll just call it t, and it can be represented using this kind of continued fraction. So here, there's actually should be an a naught sitting here, but because theta is somewhere between 0 and 2 pi, is a naught is 0. But this is the continued fraction expansion, and you can truncate it at level k. So you get pk over qk, which is the rational approximation. And a natural question to ask is, how good do these approximations get? And how do you quantify a good approximation? For one, it should be close to the thing you're trying to approximate. And secondly, you don't want the denominator to be too big. So these are the notions here. You have L of t, and it's simply the denominator times how close you are to the actual thing. So this is the Diophantine approximation type Lagrange constant. So what do we know about these things? So we know that these numbers are between 0 and 1 over the square root of 5. For example, the types of the golden ratio are 1 over root 5. And this is 0 for most numbers in a measure theoretic sense. But if you're given a particular number, for example, if you give e to the 2 pi I t and ask what are these constants for t, contemporary number theory is just inaccessible to contemporary number theory. So from our definitions and what we know about these numbers, these are inequality, and if g of n goes to 0 as 1 over n, then we can show that we have infinitely many solutions. And in scenarios like these, we get decidability results. If somehow g of n is 1 over n square, then the number of solutions really depends on these constants, which are number theoretically hard to compute. So we can sneak the computation, a query of computing these constants into an instance of our robust instance of positivity. And here's how we get the number theoretic hardness intuitively. And on the other hand, if g of n goes exponentially to 0, like 0.99 to the n, then this will have only finitely many solutions that can be effectively enumerated. And this is it's actually non-trivial, and it's actually a consequence of Baker's theorem, which is profound mathematics, so much so that in the 1970s it had earned Baker the Fields Medal. And so that's how we solved, and at a high level, how we solved robust uniform positivity. And now we revisit the picture for non-uniform positivity. And the only case worth talking about is when the ball is nestled in the cone, because here there are infinitely, actually uncountably many critical points. And how do you deal with them all? The answer is you don't. It's always a no instance when this scenario happens. And the key technical lemma here, which has a surprising amount of number theory behind it, is that if g is strictly decreasing, then this inequality here, you consider this inequality here, and this is parameterized by phi. This phi typically is the parameter of where you are. If you have a ball nestled in the cone, the intersection is an interval. So this phi comes from this interval. And this lemma says that in any non-empty interval, you're always going to find a phi such that this inequality has infinitely many solutions in n. And because this has infinitely many solutions, there's always a point on the boundary that has infinitely many violations. And so the neighborhood as a whole cannot be robustly ultimately positive in the non-uniform sense. So to summarize, here is when we can execute these plans. I told you a lot of plans. So robust positivity, robust uniform ultimate positivity, and non-uniform ultimate positivity. And in the general case, we can decide stuff up to order 4. That means the order of the LRS is 4, or equivalently, the dimension of the matrix is 4 cross 4. And already in some cases at order 5, we have this Diophantine hardness going on here at order 6. And for simple LRS, it is a little bit more promising. In some problems, we can solve up to order 5. Uniform ultimate positivity, actually, thanks to the state of the art, we can solve at all orders. So these are the results. And one question I anticipate already is, someone might have noticed that the neighborhoods that we had were closed neighborhoods. For most of these problems, it doesn't make a difference whether you take them open or closed. And well, if you still have a doubt, we can talk about it offline. But yeah, these are the results. And well, that's the talk. And I thank you.
So thank you for your talk. Are there remarks or questions?
Yeah.
So do you have complexity low bounds? Do the complexity low bounds for the normal settings translate to the robust setting?
I am not entirely sure of that. So in the paper, I do this for real algebraic numbers. Typically, the works do it for rationals or integers. So I'm not entirely sure about how the arithmetic with these real algebraic numbers works out, because that is going to be a bottleneck.
But if you restrict yourself to rationals, would it translate?
I think because of the way these neighborhoods are defined, you're still going to end up doing arithmetic with real algebraics regardless. And there, in the precise instances, you have these p-space results. And this basically comes from the fact that you can do pos SLP with integers very efficiently. But I do not know of such an analogous result for real algebraics. Okay. Yeah, this is a question in the front.
So let's say starting from this motivation, if you kind of think you perturb your drone, like you allow it. So what if you perturb it by some kind of Gaussian distribution, or like looking more practical?
Okay, so
does it make sense to consider such scenarios?
You mean the shape of the neighborhood is different?
Well, let's say perturb the initial point up to some Gaussian distribution, and then ask what's the probability will never sink below sea level.
Okay, so you want a probabilistic analog of this. So that's tricky. Off the top of my head, I don't know how to answer the question, but maybe if one writes down your initial point really is a distribution in some sense, and you do want to do arithmetic with that.
That sounds tough mathematically, but
well, so in some sense you want it still will be discrete, because at some point when you make the neighborhood big enough, you'll get into the place where it's not satisfied. So I think
I would like to ask, what's the probability you will sink? Yeah, because
so because you're doing with probabilities, you can still use this approximate picture of when things are positive and when things aren't. Yeah, so what you really want to compute is the probability you'll fall into this nice region and the probability you'll fall in this bad region. So I think it is, once you're dealing with probabilities, it's a simple first order query to, compute with what probability you fall on which side of where you fall relative to the cone. So I think that's doable, yes.
Yeah, so in the critical lemma I use and 1 minus cos and theta. Yeah.
Yeah.
Yeah. So what kind of GNs are possible?
Anything that's decreasing, like anything that's decreasing and is asymptotically zero.
So it comes from the B, right?
Eh, what's
Like
the B?
you want to ensure that UN and VN are positive.
So this is for non-uniform. So it's not the UN and VN were in the strategy for the uniform case. So this is the non-uniform case where we first compute what approximately what is the region where it's ultimately positive, and we want our ball to be in that region. So G can be anything that's decreasing and asymptotically zero.
Thanks.
Uh, in your in part of your proof, you talked about mapping your neighborhood that you have to the Euclidean unit
Yeah,
ball,
all
right?
the
Using a
way.
matrix transform.
Yeah, all the way here.
Yeah. So could you comment on the hardness of finding such a transform in the first place for any neighborhood that you have?
Because the neighborhood itself is this R transpose sigma R.
Yeah.
So you just the sigma is promised to be positive definite. So you just factorize that matrix, and it's basically that matrix which comes from this BB transpose factorization of a positive definite matrix.
Okay.
Do you have for the diagonalizable case, like the ultimate positivity that the table that you had?
Yes.
You mentioned that the diagonalizable, the simple case is decidable, right? There exists an algorithm
Yeah.
in the normal setting.
Yes.
Is it also true for the robust settings?
Yes, for simple LRS, robust uniform ultimate positivity.
No, I'm saying like there, for arbitrary order, right? Not just order 5.
Yes, so ultimate is decidable at all orders.
All order. Okay.
Yeah, even the robust thing is this. These are
I see.
like the results of this talk.
Okay.
Yeah,
Okay.
so we can do ultimate for all orders. Yes,
I see.
when the thing is diagonalizable.
And the same techniques, like
Yeah, the same techniques. Just the state of the art. It's pretty much an API call.
Okay.
Last question or remark? So this end this session. Let's thank the two speakers.
Wait, how much do I have to write? No, only this. That's it. One is for recording, one is for streaming. There's no other. Yeah, I see. Yeah.
Now, can you hear me? Okay. Yeah, cool. Should I hold it or put it in the bucket? How? Okay. Thank you. Okay. It's fine.
एक ही बटन हाँ एक ही दूसरा सेकंड बटन नहीं वाह
Hello.
Okay. Welcome to the last track B session of this year's FSTTCS. So we have two speakers in this session. Our first speaker is Daniel Asa. So Daniel, please.
Thank you. So I'm Daniel, and I will present you this joint work with Shaul Almagor and Udi Boker. In this work, we looked at the model checking synchronized CTL over one counter automata. What is already known is when relaxing the problem to a weaker variation, like using weaker structure instead of one counter automata, or using a standard CTL instead of the synchronized CTL, we get a problem in problems in a P space. And we have two results. One, we show that the model checking synchronized CTL over OCAs is decidable. We show it by reduction to Pressburger arithmetic, but yet the reduction is non-elementary. So then we focus on a central and natural fragment of the problem and show that it is in a X space. So we do some backgrounds, like talk about model checking, crypto structures, and OCAs, CTL, and then we show the results in our algorithm. So we start with the model checking. What model checking is? So model checking is to check whether a given system is satisfied by a given specification. The most basic case, the most basic branching time model checking setting is when the system is described by a crypto structures and the specification by CTL formula. This is known to be in P time. When we extend the system to be described in OCA, then we get a problem we get a problem P space complete. And when we keep the system with crypto structures and extend the specification to synchronize CTL, we also get a problem in P space. And when we extend both the system and the specification, so that is what we looked at in our work. Now let's talk about crypto structures and OCAs. So a crypto structure consists of a finite set of states. One of them is an initial state, transitions between the states, and a state labeling over a finite set of atomic propositions. To make it easy for the examples, we use these three colors instead of the labels. So let's pin this crypto structure. We use it as our example. And we talk now about computation trees. So the computation tree is the unfolding of all the crypto structures path. It starts with the initial state, and it continues, and every node that corresponds to a state S in the crypto structure, it continues with its outgoing transitions. Yeah. Because it can have, we can have two states with the same labeling, because the labeling is different from the states. Yeah, I will show you. Let's kind of go back. So in that case, the purple is P and Q, which are atomic propositions. So also S0 can have it, and also S3 can have it. And basically, we are not limited for a specific labeling. So that way, we're expanding the computation tree. Sorry for that. Stuck a bit. Okay. And these are the first 7 layers of the computation tree. Note that every path in this computation tree is also a path in the crypto structure. More examples. Okay. Now we extend the crypto structure to OCA. We show how to do it, how we do it. So one counter automata, it involves a counter. So we have initial counter value. The transitions have effects. It can decrease the counter by 1, or increase it by 1, or none. It can not affect it. And the transitions also have guards. In our case, it can be greater than 0, equals to 0, or greater equals to 0. And for every path, we must have a non-negative counter value. Meaning, if the counter goes below 0, then the path is cut. So let's take a look in its computation tree now. we start with the computation with the underlying computation tree, underlying Kripke structure computation tree. And in this case, the nodes corresponding to a configuration, which is state and counter. And as you can see, for example, the S2 node has counter 0 now because this transition, the transition decreased by 1. And here you can see an example of a transition that cannot be taken, the red one. And this happened due to the negative value of the counter, like 0, -1, then we must stop. Another example of non-taking transition is by the guard, and so on. It starts. Okay. So now let's talk about CTL and synchronized CTL. So this is the standard CTL. It's a breaching time temporal logic. It has depth quantifications, all and exist, and temporal logic, mainly next and until. We have also the finally and globally, but they can achieve by the until. There is a small description, and also they exist formulas. The semantic of CTL is corresponding to computation trees. So in this example, we have all blue until red. So the left computation tree is satisfied, while the right tree is not. And other examples. Okay, and now we get to synchronized CTL. We extend the standard CTL with two synchronization operators, until all and until exist. And now we show what is what the semantic is. So until all is maybe natural. As we can see, the left computation tree satisfied because it has a level with all red labeling. Until that, all the levels are all with blue labeling. And in the right one, there is an example of computation tree that not satisfy it. The until exist, sorry. The until exist operator is much less natural, as you can see. And we go now to our algorithms. We start with the Pressburger arithmetic. So we're solving the model checking problem of CTL plus sync over OCAs. First, via Pressburger arithmetic. Okay, so we do it by reduction to Pressburger arithmetic. So we take a CTL, synchronous CTL formula, and then by induction, we translate it to formulas in Pressburger arithmetic. These are Pressburger arithmetic formula is holds if and only if that OCA with the initial counter V satisfies phi. So the induction is on the structure of phi, meaning every step of the induction is about its sub-formulas. In each step, we're handling the sub-formula, for example, phi tag. And we get that this reduction is exponential in the size of phi tag and A. So we get some tower of exponents and got non-elementary complexity. So we focus now on the model checking problem of CTL plus until all operator only. And we use it, and we do it using a segmented periodicity. Okay. We based on the approach of GL13. We took their proof or solution and we extend it for our purpose. So I will explain a bit the approach, the challenge for us, for our work, and the resulted solution. So in their work, they find some way to calculate a threshold T and the period P. It's for the counter. And and the way to use it, how they use it, is when there are two configurations that differ only by the P counter, by P value of the counter, and the both counters above the threshold, then they have the same satisfactions for the formula. This gives us the ability to unfold the OCA into other crypto structure, where the states are configuration until that below the counter values T plus P. And then we can model check it in the known ways. So they do it by induction as well. I will show some illustration next. And for they do it like by showing construction of path from one counter value to another, and vice versa. And they do it by sub-formulas. So this is some illustration of counter values. And here is threshold 1, threshold 2, and we have the atomic propositions. And this is examples of some super formulas that for counters that above T1 satisfies, they agree about the satisfaction, as long as they have a difference by the counter of the period. So this is the simple example of how they construct it. So they look at some path from counter V, and then they construct it to counter V plus P. This is the simple way. It has more difficult cases. And for our purpose, we're talking about synchronization operator until all. And the core difference between the CTL operators and the until all operator is that the until all operator relates to a multiple paths of the same length. So the length are matter for us. And then we need to construct the paths in a way that their length are corresponding to each other. So, yeah.
The steps.
So, do you mean this threshold? So this is the threshold, and this is the complex, the more complex case of their construction, because it goes below the threshold. So they cannot rely on the induction hypothesis. So they need to adjust the length. Our solution based first, it's based on on result of LS20 that make us can be focused only on flat paths. And then by analyzing the cycles and the slopes, we can show that all ACAs admit to segment periodicity. Okay, so now I'm gonna show what segmented periodicity is, and for do it, we don't care about the computation tree itself. We care mainly on the level labeling. What is the level labeling? Like the first level is just blue, so we have just blue. The second one we have blue and green, so blue and green, blue and green again, so and so. So we focus now on the level labeling. And we show that when we take a look in the level labeling, we got some threshold, and then we got some period. You can see the threshold length is 4. We have 4 levels, and then we have period of 2 levels, and then copy of those 2 levels, and then it starts another segment. We have segments, and a new threshold starts with the same length of the previous threshold, and then we have another content for the period, but the lengths are keeping like the previous lengths. Sorry. Okay. Some points about that segmented periodicity. So the number of segments is polynomial in the size of the OCA. Sorry. The threshold and the period only depend on the OCA and the CTL plus Antilor formula. The segments can have different length, and the last segment is infinite. And if we compare two computation trees with the same initial state, that the value, the initial counter value differ only by the counter period. So we get the same level labeling. As you can see, we have the segment 1, and then we have segment 2, segment 0, sorry, and then segment 1, and then segment 2. And the level labeling is keeping in the same position in both trees. So for summary, the model checking synchronized CTL over 1 counter automata is decidable. The model checking CTL plus until all over 1 counter automata is in X space. And the computation trees of 1 counter automata admit segmented periodicity. Thanks.
Questions? Okay, so I have a couple of questions. So your OCA is non-deterministic, right? You are assuming here to be a non-deterministic OCA. So what if you consider a deterministic OCA? Is the problem, are you going to get something, some simpler complexity results? Or?
I'm not sure, and I'm not sure what is the motivation to check synchronization in non-deterministic.
Sure. And on the other hand, if you consider, let's say, push-down automaton, then
So I think that it can shown that there is reduction easily. Maybe we get some, we can find some reduction from push down automata to a bigger one counter automata.
Okay. Yeah.
Hi, so we know that model checking for CTL, like the results are known and it's like polynomial time. So what makes synchronizing CTL over one counter so difficult, like so difficult compared to normal CTL?
So the model checking CTL over one counter automata by itself is p-space. It's not p-time. The p-time is while using a Kripke structure. And it probably involved more complexities. So it became X-space.
Thank you.
Other questions? Okay, so if we do not have any other questions, let's thank the speaker again.
Hello, hello, yeah.
Escape. Yes. No, just exit, stop share. It happens sometimes. You just have to keep doing it. Cheers. No, detecting the second screen. Could you maybe remove the HDMI entire? Yeah.
Okay. Yeah.
I think you can stop the screen sharing and share again.
Okay.
Yeah. No share. HDMI. Yeah. Not detecting the second one.
Oh, is it? Doesn't that one work? Can you check this?
Okay, I might understand.
I can see there. Plus, yeah, I have this.
Sorry, audio also not. Audio also not. Okay. Can you talk once?
Hello? Hello?
Sorry, sir.
Hello?
Okay, sorry, out of person now. That's all.
Okay, so welcome to the second talk of this session. This talk will be given by Ashwin Bhaskar. Yeah, sure, please.
Hello all. I'm Ashwin Bhaskar from Chennai Mathematical Institute. Today I'll be presenting our work Constraint LTL with Remote Access. This is a joint work with my PhD supervisor Praveen, who's also from CMI. Let me quickly go over linear temporal logic. Most of you might be aware about the syntax and semantics of this. So you have these propositional atoms, you have the Boolean operators, you have the next operator, the until operator, and you have the standard derived operators, which are eventually and globally. Models for LTL, if you notice, are infinite sequence of truth valuations. So for example, if you have a formula that says globally P implies next Q, a model for the formula would be something like this, where whenever P is said to be true, the Q is also said to be true in the next position. So this model satisfies this formula, and this model basically looks like an infinite sequence of truth valuations. Now, propositions in LTL, as such, do not have any meaning, but they can stand for constraints. They could stand for various things. For example, they could stand for constraints of some form. Say the value of x in the previous position is less than the value of y at the current position, or the value of x equals the value of y in the last to last position. Basically, it can there could be constraints which compare values of variables across positions. So that is an extension of LTL. It's called constraint LTL, and where the propositions are replaced with constraints of this form. So for example, you can consider a formula which says starting from the second position, globally, the value of y is greater than the value of x at the previous position. And consider such a formula over the domain of integers. So here, if you notice, this sequence of valuations for x and y forms a model for this formula. Why is that the case? Because if you notice, at 2 is less than 3, 4 is less than 5, 6 is less than 7, 8 is less than 9, and so on. So this model satisfies the formula. So here models look like infinite sequence of valuations for these variables over some domain. If the domain is D, we can call it an infinite sequence of D valuations. CLTL, constraint LTL, has been studied, and it has been proved to be decidable. The satisfiability problem for this logic has been proved to be decidable over the reals, natural numbers, as well as integers. Here, constraints can only compare values of variables at positions that are at a bounded distance apart. So, for example, you have these constraints of this form, which says x less than previous y. I could have x less than previous y, and so on. But notice that the number of positions spanned by these constraints is given by, it can be bounded, and it's given by a parameter in the formula. But what in general, if I wanted to compare x with a value of y at some position, which is at a distance that is unbounded, at an unbounded distance. So we would like to have some operator for that. And before going into the syntax of such a logic, let me try to motivate why we were looking for such operators in the first place. So consider an online bidding forum where there are two types of messages by the bidders. One could be a request for the current highest bid, and the other is a new bid. So, and we wish to verify that every new bid is greater than the current highest bid. So, suppose some bidder bids a value B, and then there is a sequence of requests for the highest bid, current highest bid, and then another bidder bids some value B. Another bidder bids some value. So we wish to compare the value of the bid at the last position with the value of a bid at some previous position, which may not be at any bounded distance. So what we do over here is we introduce, so these R and B come from a finite alphabet of 2 letters. So we introduce the operator R star B inverse to access from the last position. From this position, we wish to access this position, for which we use this operator R star B inverse, which basically reads the regular expression R star B and looks at the minimal match for it and accesses that position. So I'll get into the formal syntax of this logic. So yeah, sorry.
So that position had the minimal position that you said. It has the last smaller bid, or
in this model, that was the previous bid. Yeah. So, and because it starts from that B, that was the highest.
But then what do the R's denote here?
Sorry. So B and R are basically just 2 types of messages. So there is either a bid message, it just denotes the type of the message. So it's either a bid message or a request message, basically. Yeah. So now let's look at the formal syntax and semantics of this logic. So we have terms. So we have variables, a finite set of variables, and we have a finite set of regular expressions coming from a finite alphabet sigma. And a term is an expression of the form E inverse X, where E is a regular expression and X is a variable. And constraints in this logic are either of the form T1 less than T2 or T1 equals T2. And the syntax is pretty similar to LTL, where instead of the propositions, atomic propositions, you have these constraints. So let me explain the semantics of this logic with the help of an example. So consider a model where there is a bid, and then there are a sequence of requests, and then there is another bid. B denotes so here we are considering a model with just one variable V. So V denotes the value of the bid. So we don't care what the value of a request should mean. We can we don't necessarily care about it. So I denote it using a star. So suppose that the value bidded in the first position was 100, and the bid value at the last position, at this position, is 200. So consider this position, and suppose I'm looking at this constraint R star B inverse V less than B. So what does it mean for my model sigma at that position I to satisfy this formula? So what it means essentially is, look at the position I, read the regular expression R star B. Here I'll hit the position B with the value 100. So R star B inverse V evaluates to 100 and V evaluates to 200. So 100 less than 200, and hence this formula is satisfied. But notice that there are some subtleties in the semantics. So for example, consider this model where I have a sequence of requests and then a bid of value 200. And now suppose I ask, what is the is the constraint R star B inverse V less than V satisfied at the marked position? Then what you do basically is, from the ith position, start reading R star B, but you'll find no match for this. And since there is no match, there is an ambiguity of whether it should be interpreted as true or false, and we assign it to be false for the case of our logic. So here we interpret this formula, this constraint, to be false at the ith position of this model. Now consider a slightly different example where there were initially 2 bids, 300, 100, and then a sequence of requests, and then another bid of value 200. And now again at the ith position, we wish to check if R star B inverse V is less than V. Now you start reading R star B from the ith position, and then there are 2 possible matches, either the first B or the second B. So there is an ambiguity as to what we choose, what we need to choose, but the ambiguity is resolved by saying that we look only for the minimal match for the regular expression, or minimal or the latest match for the regular expression. So it is going in the reverse direction. Yeah. So the it should stop at the 100, but okay, right. Yeah. So yes, you are right over here. It should stop at the 100. So for example, R star B, there's a problem with the example. It should have been R star B star, in which case there would have been two matches. So consider the expression to be R star B star inverse, V less than V. So there would have been two matches, both 100 and 300. And in that case, in order to resolve the ambiguity, we choose the minimal match for the regular expression. Yeah. So in this case, the formula evaluates to true because 100 is less than 200. Notice that RCLTL, as I've defined now, extends the constraint LTL, which is because the X inverse operator, just the previous operator, can actually be replaced by saying sigma dot sigma inverse. I read any letter and then I read any letter and go to the previous position. So similarly, X to the minus K can be replaced by sigma dot sigma, sigma K plus 1 to the minus 1. So these are the results we have. So we have two decidability results. The satisfiability for RCLTL turns out to be decidable in both the cases. In the first case, where the domain that we consider is dense and open. In the second case, over the integers. Let me give you a rough insight into the techniques that first of all, CLTL uses for their satisfiability procedure. So this technique, which is something we also adapt. So we call this technique can be broadly called symbolic model technique, where a symbolic model is a model over a finite domain that abstracts the concrete model. So this is a technique that has been used to prove the decidability results for CLTL. So I'll get into the details. So consider CLTL and consider a formula which uses X inverse, but does not use anything like X to the minus 2, X to the minus 3, and so on. So consider a concrete model which satisfies this formula, which satisfies some such formula which uses only X inverse. And now we construct a symbolic model corresponding to this concrete model as follows. So we have minus 1 and minus 2. The values of X are minus 1 and minus 2 in the first and second positions. And note that minus 1 is greater than minus 2. And so that is captured with the help of this edge marked with the greater than relation. And the value of X is less than value of Y at the first position, which is captured by that edge in the symbolic model. So basically what we do over here is, since the formula can span at most two positions, so since the formula has only previous X inverse operator, it can span at most two positions. And so we consider all variables in consecutive pairs of positions and capture all edge relations between them, which the concrete model satisfies. So for example, over here, row 1 captures all the edge relations that the first two positions of the concrete model satisfy. Similarly, row 2 captures all the edge relations satisfied by the second and third position in the concrete model. Row 3 captures all relations in the third and fourth positions, and so on. So notice that we can generate a symbolic model rho, which equals row 1, row 2, row 3, and so on. The important thing over here is that each of these row i's comes from a finite alphabet. Why is that the case? Because given any pair of positions, there is at most 3 to the 6 possible edge relations between them. Because given any pair of variables, given any pair of positions, there can be just 3 possible edges. Given any pair of positions, there are 3 possible edges, a greater than, a less than, or equal to. And since there are 6 combinations, You have at most 3 to the 6 in the worst case, for possibly many edges. So each of these rows comes from a finite alphabet, and hence row is a sequence over a finite alphabet. And we define the symbolic semantics. So given a symbolic model, we say row, the symbolic model row at the second position symbolically satisfies the constraint previous x less than y, because if you notice, you have that edge from the first x to the second y. And the interesting thing over here is, in order to check for this symbolic satisfiability, I need to look at only one letter, which is row 1. Compare it with the concrete model. If I had to check if the concrete model sigma satisfied this same constraint, I would have had to look at the value of x at the previous position, the value of y at the current position, and then compare them. But in the symbolic model, I have row 1 given to me, which captures all the edges. I just look at row 1 and query if the constraint x inverse x less than y is contained in row 1. And we need to look at only one letter for every constraint, and hence checking the symbolic satisfiability of the formula itself is very similar to checking the satisfiability of an LTL formula, because these constraints can be thought of now as atomic propositions, and symbolic satisfiability is equivalent to checking satisfiability of LTL over these atomic propositions.
Just to ensure that I'm following you correctly. So when you say finite alphabet, the alphabet size has increased now.
Yeah, the alphabet size is increased. Yes, the alphabet size is possibly some 3 to the 6 in this case. In fact, the formula could be more complicated. So I could have x raised to minus 2, x raised to minus 3, where I would have edges from this x to this x to this y, and so on. The graph will have more edges. Yeah. So it would be nice if satisfiability of CLTL would just reduce to the symbolic satisfiability. That is, if I could just check if a symbolic model satisfies this formula, and if that were enough to guarantee satisfiability of CLTL formula, that would have been good. But it turns out it's not the case, which is because suppose phi is consider phi to be some symbolically satisfiable formula, and let row 1, row 2, row 3, and so on be a symbolic model which satisfies this formula. Suppose row 1 is of this form, where you have these edge relations, and row 2 is of this form. Notice that row 1 imposes the condition that the value of x at the second position must be less than the value of y at the second position, whereas row 2 imposes the condition that the value of x at the second position in the entire model should be greater than the value of y at the second position. So these two constraints essentially clash with each other, and hence row 1 and row 2 cannot be placed adjacent to each other in the symbolic model, as that would lead to an inconsistency. So what we would require then is to check if the symbolic model, it is not just enough for symbolic satisfiability, we also need to check if the symbolic model at hand is actually consistent. And checking for consistency turns out over here is actually not that complicated. So what we just need to do is consider a row I and a row I plus 1. Since there are only finitely many possibilities for row I plus 1, we list all the row I plus 1s that are compatible with row I, and just check if this sequence this pair of row I and row I plus 1 lies in that set of compatible frames. So we could call these row I's as frames. So which means that checking for consistency can be done actually by a finite state automata. So are we done? So if we have a symbolic model that symbolically satisfies a formula, and if we have a mechanism to check for consistency, is it enough? Will it then turn out that actually we can reduce the satisfiability problem to checking for symbolic satisfiability? It still turns out that there is a case where this won't work, which is, for example, consider a symbolic model where y is less than x. And notice that there is a chain of length 3 connecting y and x. So you have y less than this y less than x less than x. And there is also a chain of length 5, there is a chain of length 7, and there are chains of ever increasing lengths. So there is no bound on the length of the chain of any chain between y and x over here. which means if we are in the domain of integers, I cannot assign any value to x and y, even though this symbolic model may satisfy the formula symbolically, and even though it's consistent, there is no value that can be assigned to x and y, which can actually such that, I mean, there is no way I can come up with a concrete model that actually corresponds to the symbolic model, which is the case over the domain of integers, because there cannot be two integers with unbounded distance between them, with infinite distance between them. But for the case of dense and open domains, such a problem does not arise. For example, over the real numbers, this problem does not arise because I can actually assign 1 to x and 0 to y, and then assign a decreasing sequence of values to the following x's and an increasing sequence of values to the y's, such that both these sequences converge to half, for example. So this, even though over here, this actually satisfies the symbolic model, and I can actually assign values to x and y over here. But which means that for the case of the concrete models, I can actually construct a decision procedure. I check for symbolic satisfiability of the CLTL formula, which is now viewed as basically an LTL formula. And I also check if these symbolic models are consistent, and I'm done. So the satisfiability for this CLTL reduces to a satisfiability problem over LTL. I'm not going to the details of it, but then this roughly is the idea. But for integer domains, we also need to check whether a symbolic model has unbounded chains of this form that we saw over here. And this also turns out that it can be done using a finite state automaton, provided the symbolic model is ultimately periodic. So it turns out that if the symbolic model is ultimately periodic, we can identify patterns, which repeatable patterns, which guarantee the existence of unbounded chains. And those small repeatable patterns can be detected using a finite state automaton. So these were based on this technique, Stefan Demry and Deepak D'Souza give a decision procedure for CLTL over the integers as well. Now let's go back to CLTL with the remote access, our logic. So here a concrete model looks somewhat like this. Let's take an example where there is just one variable again. So I have a bid message, I have a sequence of request messages, I have another bid. The first value is 100 and the last value is, the marked value is 200. And now suppose I wish to check, now suppose I wish to construct a symbolic model for this concrete model. The problem over here is, unlike in the case of CLTL, where I had this notion of frames, where I could compare variables across a bounded range of positions, here I do not, the value of B, the B over there is could be unboundedly far apart, and there is no frame of a fixed size that can capture all these edges. And hence, what I choose to do over here, what we choose to do over here is to, capture the relation R star B inverse V less than V at that position. So we essentially capture this relation at that position, which says that if you read, since there are a finite number of regular expressions and there are a finite number of variables, there can be a finite number of possible relations, finite number of total such possible relations. And at every position, we store some subset of these relations. And we call that a memoir. A memoir is a subset of such relations that are stored at every position corresponding to the concrete model. So a symbolic model looks like this, and suppose we ask the same question over here. Does satisfiability for CLTL reduce to symbolic satisfiability? And since it's more general than CLTL, it turns out no. And in fact, it's more complicated over here, because, for example, consider two symbolic models. The first symbolic model having the relation E1 inverse x less than E1 inverse y stored at the jth position, and the second symbolic model having E2 inverse x greater than E2 inverse y stored at the kth position. And suppose now that E1 if you read even from starting from J backwards, I is a minimal match. And if you read E2 from K backwards, again the same I is a minimal match. Now this essentially means that you have a symbolic model along which there are two memoirs at positions J and K, one of which wants that xi should be less than yi, whereas the other imposes that xi should be greater than yi, which leads to an inconsistency, just as in the case of CLTL. But now the difficulty is that the inconsistency is not captured by consecutive row i's as we did over there, whereas there could be memoirs that are at a distance, unbounded distance apart. For example, J and K over here need not be consecutive positions; they could be unboundedly far apart. And memoirs at these positions capture inconsistency. So, in order to check for inconsistency, I may have to go along the model and check for memoirs at which are pairs of memoirs which are unbounded distances apart, just to check for this inconsistency. But it still turns out that the consistency check can be done using finite state automata. And here we use the fact that finite state automata are equivalent to monadic second order logic over words. And we actually write an MSO formula that captures this contradiction. So given a symbolic model, what we loosely want is that we do not want positions I, J, K such that there is a memoir at J which says xi less than yi, and there is a memoir at K which says xi is greater than yi. So yeah, so we wish to this is a rough version of the MSO formula. The actual MSO formula is more complicated, but this is what the MSO formula captures. This is how the MSO formula captures the inconsistency in the symbolic model. So the previous, so even if we have consistent symbolic models as before, over the case of integers, our problem persists. So we may have these the value of, I mean, we may have y less than x and chains of unbounded length between y and x. And over the integer domain, no value can be assigned to x and y because they are infinitely apart. And again, it turns out that for the dense open domains, this problem does not arise. And in fact, just checking for consistency of these symbolic models turns out to be enough. So checking for symbolic satisfiability and checking if the models are consistent actually gives us a decision procedure for RCLTL over the domain, over dense domains, which includes the real numbers. And hence, we get a decision procedure there. But for the integer domains, again, we need to check whether a symbolic model has these unbounded chains, which I showed before. And this can still be done by finite state automata, provided the symbolic model is ultimately periodic. And here again, we use the fact that these finite state automata can be, I can write MSO formulas for them. And we basically write MSO formulas which detect these small repeatable patterns. And we also prove, which involves a fair bit of complication, that these ultimately periodic symbolic models in this case actually have such repeatable patterns, detecting which then finite state automata can detect to detect the unbounded chains, presence of unbounded chains. So I'll not be going to the details of these due to lack of time. Yeah, that's it. Thank you.
So time for questions.
Yeah, thank you for your talk. So I think I might have missed something. Why was it necessary that these checkings were done by FSAs?
I mean, we need some decision procedure to check these. It's not necessary that these be done by finite state automata, but usually automata theoretic techniques are used in, over here. And I mean, so for CLTL, it was done using finite state automata, and we tried in our model also to use finite state automata, and it worked.
Okay.
Yeah. But yeah.
So as sort of a follow-up,
yeah,
wouldn't it have been easier to use slightly more powerful models of computation though? In the sense of it might have been easier to, would it have been easier for the proof to work, or would it have been, does this make it easier?
Not very sure, because finite state automata are very easy to handle as such.
Okay,
I mean,
okay.
it's immediate to construct finite state automata or MSO formulas for these cases.
Okay, okay.
Constructing some other model, I mean, converting to some other model might be much more difficult actually, but yeah,
I see, I see.
we haven't experimented.
Okay, thank you.
Other questions? So I was just wondering that here you were considering some kind of a linear order, right? The domain
Yes, the
are
domains
linear. So are there similar works where you can consider, say, trees and branching time logic constraint?
Not exactly well, but what I know is that even CTL has been extended with constraints. So
Okay.
there are CTL with constraints.
Okay.
So there is some work on that. There is some pretty theoretical work on that. I think there are techniques which are not automata theoretic, more mathematical, which have been used used in such cases as well. So
Okay.
I think. Apart from that, not just over natural numbers or integers, even over strings. So for example, you could instead of these the linear order, you could have relations like prefix or subword, and there is some amount of work for extend where LTL has been extended over such domains. Constraints are of those forms.
Okay. And somehow this also reminds me of like words with like the data words kind of things, like
Right, yes, yeah.
say for example freeze LTL or
yes,
data automata, these kind of things. So are
Right.
there any relation?
Yes. So freeze LTL, for example, I would believe it's much more powerful than this, because there you can compare values of variables across unbounded positions. That is something we do here, but you can even have negations of such things. So I can say that the value of X is not less than the value of any other Y in the future.
Nice.
Whereas here I just look to one Y still and say that X is less than that Y. So in that, that way it's more powerful. And also it's more powerful, I guess, because I can also talk about the intermediate values between these two values in, I guess, in LTL with freeze operators. Those are allowed, which is why I guess it becomes undecidable in the general setting and we need to look for fragments over there. Yeah, data automata, I'm not exactly sure how it compares with this.
Okay. Other questions? Okay, so if there are no more questions, let's thank the speaker again. So this concludes this session, and yeah, thanks to both the speakers of this session for the wonderful talks. I don't think I have anything else to announce. Thank you. Yeah, it's lunchtime.